Hi everyone. I know I've said this a bunch of times in class today, but let's start off with a concrete example. If you didn't know something's mass and you didn't have access to a scale, or you're in the depths of outer space where you can't do gravitational you can't do a gravitational mass, but you could calculate its inertial mass, right? And so, for example, if you had to know the mass of this rock out in outer space for some reason, and you applied a 20 Newton force, and after 10 seconds, it's sped up by 10 meters a second, well, then we know some stuff. We know that the force on it, presuming it's the only force, that is the net force, is 20 newtons. And we know that the acceleration was the change in velocity per time. It went 10 meters a second faster in 10 seconds, which makes the acceleration 1 meter a second faster every second. Right? And we've got F and we've got A, and we know that the summation of the forces causes that mass to accelerate. And again, if that's the only force on it, then the net force, the sum of the forces is 20. And so we just say the mass of the rock is, mass is force over acceleration, is 20 newtons over 1 meter a second squared. Makes the math nice and easy. That's a 20 kg rock. Okay. And then I know that I said that a bunch of times in class. So let's keep cracking here and go to the next page. Get my cursor over there. There it is. And so here's an irregularly shaped wheel like the one set up at Lab Station 1 earlier today. It had a constant 10 Newton force. It was that wheel that looked like this, and it had the weights here, right? It had weights, and we moved the weights around and talked about the moment of inertia. It had the pulley in the center, and we rotated it around, right? That wheel. And I was saying stuff like, you don't want to calculate the moment of inertia of that mathematically. You're better off doing it dynamically. And by that, I mean the same thing we just did with the rock. So let's see here. 10 Newton force, 4 centimeters from its hub. So the force you apply to this wheel to get it to spin is a 10 Newton force. And the radius, the distance it is from the center, the axis of rotation, is 4 centimeters, is 0.04 meters. And then, and so it starts from rest. I don't think I explicitly say that, but it starts from rest, and after 5 seconds, it has an angular velocity of 77 RPM. Okay, good. And then, so let's go ahead and find the acceleration. But the first thing it says is state the velocities in standard units. Well, omega initial was 0, right? It started from rest, radians per second. And omega final is whatever that is in radians per second. So I don't know, let's do that quickly. 77 rotations per minute. I'm just going to write minute like that, if that's okay. Save me one step. 77 rotations per minute. And we also know that one rotation is 2 pi radians. Right? And so now, when we do this, we'll get radians per second. Right? And so 77 times 2 pi, 77, calculator into view here, 77 times 2 pi, there's my numerator, divided by 60, divided by 60, is 8.06 radians per second. 8.1 radians per second, right? So it goes from 0 to 8.1, that's omega final, right? And it does that in 5 seconds. And so the angular acceleration during that pull, during that torque, right? The angular acceleration is, well, just like linear acceleration, where should I put this? Linear acceleration is the sum of the forces over the mass. The angular acceleration is the sum of the torques over the moment of inertia. All right. And we're looking for the moment of inertia here. I guess we haven't written down torque yet, but we'll have it in just a moment. And so let's just say, okay, well, if alpha is tau over I, then moment of inertia is the sum of the torques over the angular acceleration. Now, there's only one torque on this wheel. We're not doing frictional torque or anything like that. There's no other countering torques. It's just that one torque. And the torque is R times F over alpha, right? That's the torque, is R times F. And R times F is 0.04 times 10. 0.04 times 10 right, is 0.4 meter newtons of torque, and the acceleration that we saw was 8.1 radians per second. Nope, we never calculated the acceleration yet. Hold on. The acceleration, the angular acceleration, is the change in the velocity per time. It went from 0 to 8.1, so the change is 8.1 radians per second. Here's the acceleration. Just like up here, the acceleration was change in velocity per time. The acceleration here is change in angular velocity per time. And 8.1 over 5 seconds. It took 5 seconds to do this. And 8/5 is what? Almost 1.8. 8.1 over 5 is 1.62. So we've got an alpha of 1.62 radians per second faster every second. And so the torque was 0.4, that's R times F. The alpha was omega over T, which is 1.62 radians per second faster every second. And 0.4 over 1.62 is a number, 0.4. Divided by 1.62, I'm getting about 0.25. The moment of inertia of that wheel, given these numbers, moment of inertia is about 0.247, or about 0.25, and well, the best way to do moment is mr squared, so it's kgs times meters squared. That's the moment of an irregularly shaped object. I didn't go do any calculus to integrate and find the volume or the mass distribution about the volume or anything like that. I just did what? I just did, here I did, right? A is, mass was force over acceleration. Well, here I did torque over angular acceleration. Let's keep going here. Let's see, let's do this one here. So now we're into dynamics, right? No, this is energetics. Right? This is energetics, right? So a bowling ball rolls up a ramp 0.5 meters high without slippage. So it's rolling, it's not slipping. And it has an initial velocity at 3 meters per second, right? So we better write some stuff down. Looking for my pen. There it is. Sorry. So a bowling ball rolls up a ramp 0.5 meters high. So here's my quick setup here. 0.5 meters. There's it at the top. There's it at the bottom. And what else do we know? It has an initial velocity of 3 meters a second. 3 meters per second. Okay. And what is the speed at the top of the ramp just before it hits the other balls and stops? And what maximum ramp height? What is the maximum ramp height the ball can roll up? Well, gosh, okay, we got to do this energetically. And here's the thing. Can rotating things do work? And the answer is yes. In fact, we said earlier today even that the kinetic energy rotational is 1/2 I omega squared. And the kinetic energy translational, that's good old-fashioned kinetic energy, is 1/2 mv squared. So guess what this ball has? It has both. And then up here, it has also gravitational PE, U gravitational. So the energy before is going to equal the energy after. What kind of energy does it have before it hits the ramp? It has rotational kinetic energy, and it has translational kinetic energy. It's rotating and translating, right? And then up at the top, and that's going to equal, up at the top, it's still rolling, so it's still got K rotational after the fact, and it's still moving, right, down the line. So it's still got K translational, that's after the fact, and it's got U gravitational, and it's got PE, which is MGH. Okay, this looks like a mess. Oh boy, here we go. K rotational plus K translational. Okay, 1/2 I omega squared plus 1/2 mv squared equals, equals 1/2 I omega squared prime, 1/2 I omega prime squared, that's K rotational after the roll, up the ramp, plus 1 half mv prime squared. That's the velocity, translational velocity as it glides along up top, and plus some mgh. Yeah, boy. Well, I got m's and omegas. I'd love to make those m's go away, especially because they didn't tell me the mass of the ball. So why don't we've got m's everywhere except for those two omegas. Why don't we go ahead and say that, I don't know. Let's go ahead and say that omega squared is, oh yeah, omega, well, let's see. So V tan is R times omega, right? Is that going to help us? R over V. I can get rid of some V's for us. No. Got to get rid of those M's. 1 half I omega squared. Omega is also change in angle per time. And that's the velocity. And what else do we have here? That the moment of inertia. Oh, maybe that's how we get rid of the M's. Yeah, we used to have I's in them. I, moment of inertia. Let's see, this is a sphere, so it's 2/5 mr squared. There we go. How about this? Where we see I, let's put 2/5 mr squared, because it's a ball, and it's got the same moment of inertia in both cases. So let's go ahead and do that. And how about where we see omega, let's put V over R. Yeah, let's do that. So I'm gonna rewrite this one here for omega. Omega is velocity over radius. So let's take these two and substitute them into our equation down here, where we're going to get 1 half I times omega. So 2/5 mr squared, 2/5 mr squared. There's 1 half of I, and omega squared, well, if omega is V over R, then omega squared is V squared over R squared. So omega squared is V squared over R squared plus 1 half of mv squared, and that's going to equal 1 half I omega prime squared, 1 half of 2/5 mr squared. That's the I, that's the moment. Where am I here? I'm right there. 1 half I. Omega squared is V prime squared over R squared, V prime squared over R squared. So that's the first term after the equal sign. That's 1 half I omega prime squared, 1 half I, the moment of inertia of a sphere. Omega squared, omega prime squared is V prime squared over R squared. And then I'm here plus 1 half mv squared plus 1 half m, that's V prime squared, plus mgh. Okay. Well, right off the bat, look at this. We can get rid of the m's. I've got an m in this term, and I've got an m in all my terms. I've got an m in all those terms. Make life a little bit easier. And 1 half of 2/5, well, I can do that in my head. 1 half of 2/5, well, that sounds like 1/5. So how about this? 1/5, the m is gone, right? R squared. 1/5 R squared, and then V squared over R squared, V squared over R squared, plus 1 half mv squared, plus 1 half m v squared, equals 1 half of 2/5 mr squared. Okay, 1 half of 2/5 again is 1/5. And the m is gone. Oh, the m is gone. I left the m here. Sorry. Get that out of there. We're dividing everything by m. We've got m's in all terms. 1/5, 1 half of 2/5 is 1/5. M is gone. R squared, V prime squared over R squared. V prime squared over R squared. Okay, there I am. Plus 1 half mv prime squared plus 1 half, the m's are gone, V prime squared plus g times h. Plus g times h. Okay, well, let's go ahead and keep making this more simple, right? Because look at this. Here, I've got 1/5 r squared, over 1/5 r squared, v squared over r squared. Those r squareds are canceled out. And by the same argument, these are too. So let's rewrite this again. 1/5 of v squared plus 1/2 of v squared equals 1/5 of v prime squared plus 1/2 of v prime squared plus g times h. I don't even know what I'm looking for anymore. Oh, the speed at the top of the ramp. Okay, I'm looking for v prime. Okay. Well, we can do this. Look, because 1/5 plus 1/2, that sounds like something we can do. Right? 1/5 plus 1/2. So, I don't know, turn these into what? Tenths? So 1/5 is 2/10, and 1/2 is 5/10. Right? So 1/5 is 2/10, and 1/2 is 5. So 7/10 v squared, 7/10 velocity squared equals, well, again, look, 1/2 of, we want to add these guys together. 1/2, and they're like terms, v prime squared, so we can add them up. And 1/5 plus 1/2 is what? 2/10 plus 5/10, and 2/10 plus 5/10 is 7/10. Goodness gracious, 7/10. I know I was getting into this. 7/10 what? V prime squared. 7/10 v prime squared plus g times h. And I'm after v prime, right? So let's just subtract the gh over. Right? So let's subtract that gh over, and I'm going to rewrite it like this: 7/10 v prime squared, 7/10 v prime squared, and then equals 7/10 v squared. Am I still on the paper here? Yeah. Let me move this so you can see it well. 7/10 v squared. I've lost my place here. So I just subtracted. I'm subtracting that over. So 7/10 v squared minus g times h. Minus g times h. Okay. Ooh, Dougie. Yeah. Okay. So let's just let us do this. So let's divide both sides by 7/10. I'm going to go up here with it. Let's divide both sides by 7/10. Okay, so that way I get v prime squared equals v squared minus g times h over 7/10. Or, better yet, v prime equals the root of v squared minus gh over 7/10. But let's just multiply by the reciprocal, so we don't have to look at it like that. Gosh, I just need one more little spot. I'll write it down at the bottom in red, so it stands out. So I'm gonna instead of leaving that down there in the denominator, I'm gonna multiply by the reciprocal to get it up into the numerator. And so my final equation is, how fast is that ball going? Well, v prime equals the root of v squared, its initial velocity squared, minus what? 10/7 g times h. And now it's just math. Now you just stick the numbers in, right? So now the answer would be, how fast is the ball going at the top of the ramp? I don't know. How fast was it going before? 3? So the square root of, I'll just do, so the square root of 3 squared, 9, minus, I better use parentheses here, 10 minus 10/7 times g times h, what was that, 0.5, right? Times 0.5 meters. And I get a number here, and I take the root of that number, root of answer, and I get 1.36 meters a second. 1.36 meters per second. And then I say to myself, does it make sense? Because it's got to make sense too, right? The ball was going 3 and it rolled up that little ramp, and now it's going 1.36. That sounds reasonable to me. What if I got 13 meters a second or something? Well, that doesn't make sense, right? It was going 3. It wouldn't speed up as it goes up the ramp. So I'm subjecting it to a little bit of common sense anyway, and it seems to make sense. I feel like I did my algebra right. You guys let me know if I made any mistakes, but I don't think I did this time. All right, what maximum height could the ball reach? Well, here you would just take the same equation, right? Like this one right here. Better yet, before I got the radical, here, take this one, take that one here, and just solve it for h. That's all. So, I don't know. You got to add this. You got to add that over, and then isolate the h. That's all, and then solve for h because you've got all the numbers here. You got the speed before. Oh, you would set this to 0 though, because if it goes up the ramp, maximum ramp, it's going to just get there and run out of velocity, right? So it's only going to have PE. So it's going to be. So you're not even going to have that there. It's going to have no velocity once it gets to the top. If it's maximum, going to the maximum height it can get to, right? It's going to get some maximum height and stop. Right? So that makes this easier, right? You just multiply both sides by 7/10 and divide both sides by g, and maybe multiply by -1 to get rid of the negative sign. You'll have the height it could roll up. Okay, so that's an energetics problem. That's more complex than you're going to see in your test. But let's take a look here. Angular momentum is well. Nick was quick to tell us this today. Nick said that's I times omega, and that is correct. So let's try this problem here. This is one of those problems from University of Colorado, and a student sitting on a frictionless platform. He's rotating with an angular speed of 3.1 radians per second. That's omega initial is 3.1 radians per second. His arms are outstretched, and he's holding a heavy weight in each hand, and the moment inertia of the student, the weights on the platform about the axis, is 10 kg times meters squared. So the initial moment is 10 units. And when the student pulls the weights inward towards his body, the moment of inertia decreases to 5.6. So I final is 5.6 units. Kgs times meters squared. And where are we at here? What is the resulting angular speed of the platform? Omega final is, I don't know. This is the classic ice skater move when they have their arms outstretched, the figure skater move. When they have their arms outstretched and they start spinning and they pull them in and they start spinning really fast, right? Because what's going on here is that, guess what? Momentum is conserved. The momentum before is equal to the momentum after. The I initial, omega initial, equals the I prime, omega prime. Right? The momentum before equals the momentum after. If this were a linear problem, we'd be saying the mv before is equal to the mv after. But the m's are more complicated, as are the v's, so we represent them differently. So, but you see, we have all the numbers here. This one's actually pretty straightforward. We just have to do omega final over here by dividing by I final. Omega final will be I initial, omega initial over I final. So we've got all these numbers. It's just 3.1 times 10 up top, right? 3.1 times 10 up top, which is just 31, right? And the units are I times omega, 31, and units of momentum. I'm not going to write down those units right now. I don't want to use the time of the video. But the units are kgs times meters squared, that's I, times omega is radians per second. And so radians are dimensionless, and so it's kgs times meters squared per second. I just said I wasn't going to do it, but I did. Kgs times meters squared per second. And then I down on the bottom is I final. It went down to 5.6 because why? Because the mass got closer. The mass got closer to the axis, so it got easier to speed up. As the mass gets closer, it gets easier, and as the mass gets farther, it gets harder. So the moment went down because the mass got closer to the center. I prime was 5.6 kgs times meters squared, and this was over. That's an S. And then kg times meters squared cancel. I guess I should have kept the radians in there. Now we're left with radians per second for our units, and it's 31 over 5.6. That's our answer. 31, a little bit easier than the last one. 31 over 5.6 is 5.5. And you say, does it make sense? Let's find out. 5.5 radians per second. Yeah, that makes sense. They were going 3.1. They were going 3.1. And when they brought their hands in so the moment decreased, they went up to 5.5. That sounds about right to me. Next one. Last one. Next one and final one. Here we go. Hold on, people. We're almost there. And then it's time for you to give it a try in the purple folder. A horizontal platform with a mass of, whatever I just read, 85.1 kgs. And it's a 3.41 meters is the radius, so this is big. Wow. 13, 14 feet in radius. It's a giant merry-go-round is what it is basically, right? And a frictionless vertical axle, so there's no frictional torque. And a student, 76.3 kgs. So that's the mass of the cylinder. And the mass of the student, I just read, was 76.3 kgs. Okay. And they walk slowly toward the center. The angular velocity of the system is 2.3 when they're at the rim. There we go. My pen's running out of juice, I think. The initial angular velocity is 2.3 radians per second. What else do we know? And find omega when the student is 1.93 meters from the center. Omega equals question mark at 1.93 meters. At r equals 1.9. At r student equals 1.93 meters. And use radians per second. Okay, let's see here. Okay. What am I after here? Find omega. So, yeah, omega equals, I don't know. Okay. This is also a momentum problem because the moment of inertia before times the angular velocity before is going to equal the moment of inertia after times the angular velocity after. Yeah. And so we're after omega f, right? Final. And so omega final, omega prime, will be, that sounds like some sort of supervillain, right? Or maybe a superhero. Omega prime. Omega prime, is I times omega over I prime. And so that's I initial. Well, let's find out I initial, right? So this is a little bit weird, but not terribly so. It's the summation of all the point particles. And so the 1/2 mr squared gave me the mr, will give me the mr squared, the 1/2 mr squared will give me the moment of inertia of this disk. All those little particles, whatever, it's iron or something, all those little iron particles, when you sum them, you get 1/2 mr squared for the moment. But remember, moment of inertia is the summation of all the mr squareds, right? And so this is going to be the disk plus the student. There's a particle right there. So this disk is the summation of the mr squareds. The disk has a moment of inertia of the disk itself, the metal disk itself, 1/2 mr squared, plus the point particle, plus mr squared of the student. That's going to be the moment of inertia. So I initial was 1/2 the mass of the disk, 85.1 kgs. That's m, and the disk has a radius of 3.41 meters. That gets squared. And then I add the point particle. And the point particle is the person, the student. So they are, that's just mr squared because it's one thing. The mass, the 76.3 kgs is right here at r equals, does it say they're on the rim? Yeah, from the rim. So at first they're right out of the rim at first. So so it's just mr squared. So 76.3 kgs is the person's mass, and they are also at times 3.41 meters. 3.41, those are meters, sorry. And so the moment of inertia of the disk is the summation of all the MR squareds, and so the disk plus the person, the whole thing. And so the disk itself, just the disk without the person, has a moment of 0.5 times 85.1 times 3.41 squared. The disk itself has a moment of 494.8. That's 494.78.7, carry an extra sig fig here. And those are kgs times meters squared. That's just the disk. And the person also adds inertia to the disk, and they are a point particle again, so they are just m times r squared, and that's 76.3 kgs times 3.41 squared, and I get 887.22. 887.22, and those are also kgs times meters squared. So the disk has, I'm just going to add 494.78. 494.78. The disk has a moment of 1382 kgs times meters squared. The disk has a moment of inertia of 1382 kgs times meters squared when the person is at the rim, and then they're going to walk toward the center, and that number is going to go down. And so the velocity is going to go up. Okay? So this is going to be, let's see here, omega final will be, well, I initial, that's 1382 kg times meters squared. That's the moment. And the initial velocity, it was going 2.3 radians per second. And we want to know how fast it ends up going later after the person walks to the center, where the disk will have a different moment of inertia. So the moment of inertia I prime will be, again, the 1/2 mr squared of the disk itself. We have that number. Plus the mr squared of the student, the new mr squared of the student. The student still has the same m, but they walk toward the center, so that value goes down. Okay. Well, I prime, therefore, well, we already have this, so let's not do that again. That's 494.78 kgs times meters squared. And then I'm going to add the moment of inertia of the student at their new location. Well, the student is still 76.3 kgs. But they are now at a distance of, what does it say, r prime? Do I have that somewhere? 1.93 meters? Is that what I saw? Yeah. Now they're 1.93 meters. They're not 3.41 meters. They've traveled inwards to the 1.93 meter mark. They're more like, they've gone from here to here. They walked from the edge inward, and so the disk got easier to spin, and so it would speed up. So 1.9, and that gets squared, right? And so let's see here. Let's just do that term first. 76.3 times 1.93 squared. That number is 284.21. 284.21, and those are kgs times meters squared, and that gets added to our 494.78, 494.78 kgs times meters squared. Right? And so now the new moment of inertia is 284.2 plus 494.78. My new moment is 778.98. I think I'll go ahead and call that 779 kgs times meters squared. There's my new I prime, and that's what goes up here. I prime is 779 kgs times meters squared, which gives me, I'll go this way with it to write. I'll do this math up here. Now I'm ready, and it should speed up by a bit. They were going 2.3, and they better end up going faster, or we did something wrong. 1382 times 2.3 is whatever, divided by 779, and this equals 4.1, 4.08. 4.1 radians per second. That's how fast they end up going. Did they speed up? Yeah, they did, right? Because they were going 2.3 before. and they sped up to 4.1 when they went into the center. That's good, right? And so the big point here is this, is that, if you have a disk, it's got a moment of inertia of, it's a cylinder, right? It's a short, squat cylinder, so that's 1/2 mr squared. But if you put a weight right here, you just put a point particle on that disk. Now it's 1/2 mr squared plus, let's just do this in blue. That's blue now. Well, kind of purplish, but that's okay. I just put a 1 kg mass out here, right? So now it was 1/2 mr squared without that weight, but I just put a weight out on the edge. And so now I've increased the moment of inertia of the whole thing by what? By what amount? Well, it's a point particle at a given radius, so that's just mr squared. If you laid down, I don't know, if you laid down a cylinder on top of it, then you'd do 2 cylinders. And if you had, gosh, I don't know, if you had if you had a hoop or something, a ring, a thin ring, and you suddenly put a weight on it, that'd be mr squared for the hoop because all the mass is out there, plus the mr squared of the little weight, right? So you've got to identify what it is that you're adding or taking away from the thing that resists the acceleration, the moment of inertia. I think that's a pretty good example. It was 1/2 mr squared, and it went down. It was 1/2 mr squared plus mr squared, and then later it was 1/2 mr squared plus a new mr squared as they got closer. Okay, that's that. Go try the stuff in the purple folder, and let me know about any questions. All righty, take care.